Good afternoon, this is Schweitzer. We're going to add our second problem involving projectile motion. The last video looked at throwing something just straight up in the air and coming back down. And we did that. You can also use energy to solve that problem. I didn't use it in that last problem, but we used energy earlier in the year. Now we're going to look at a problem that is throwing something. You maybe have a ball here, and you just kick it straight off a cliff, and it's going to start falling off looking something like this. Now, couple things I want to note about this, okay, is one, keep in mind that the x component controls how far you move horizontally. That's what the x velocity controls. How far, and we often call this range. And the y component controls two things. It controls time in the air. That's the most important thing. It also controls max height, which of course, if it's on a cliff, how high you are off the cliff is the max height. If we shoot this thing off the cliff at 15 meters per second, which it states right here, and we're 50 meters off the ground, the 50 meters, I'm at my max height already, which is 50 meters. Now again, a couple things we want to point out about x and y components. They work completely independent of the two. The only thing that is common between these two is time, meaning that if it's in the air for the x as it is for the y. Every single other aspect works separately. All right, so let's go ahead and list out some of these variables that we have here. First things first, we're going to use two major formulas, the distance formula. Distance equals xi plus vit plus 1/2 at squared. So I'm going to use the location. Again, s is, I refer to xt. It's the location at a specific time. vi is very common. Time is very common. Acceleration is very common. You could have a starting location xi2 also, or x0. Alright, so before we get started, anything happening here in the x component, that's how far we traveled horizontally. I can't put anything for distance because that's at a certain time. Initial velocity, 15. Horizontally. Initial velocity of y, 0. That's very important. It's not going down at all. Time, again, depends on the problem. What's the time is the various times across the entire pathway. Acceleration. Alright, so the acceleration of gravity only works in the y direction. This is negative 9.8. What's the acceleration in the x direction? I'm going to put one more thing here before we talk about that. In the initial position in x is 0. Initial position in y, depends how we set this up. I'm going to go with the bottom is 0 and the top is my frame of reference is going to be 50. So I'm going to put that this thing currently is at positive 50. Initial position of 50. And we'll go down to 0. Or you got to do 0 and then negative 50. That's the most common way you'd want to do this. All right, now let's back to acceleration. When we look at this thing, and you may have watched maybe a movie where you see something jump off, you know, a large building, and all of a sudden it looks like it just goes straight down at some point, you know. But what happens is these two things work independently of each other. So at the beginning, my velocity downward is almost nothing. And I'm going to draw a little vector diagram here. Initially, I have a horizontal velocity of 15 and almost no downward velocity. Then, as I'm falling, I'm picking up a downward velocity. And my horizontal is staying the same. So I am not gaining any or losing any horizontal velocity, but I am gaining such vertical downward velocity that makes it look like I'm losing horizontal velocity, but I'm not. Always stays the same. There's no only countering force of the horizontal is air drag, which we normally consider to be negligible at this point. So it only looks like it's going straight down because the vertical velocity is increasing at such a large rate. But so the acceleration in the x direction is actually 0. That is something that many people get misplaced with. Acceleration in the horizontal, 0. Acceleration in the y, negative 9.8. Take a look at these pieces here, and from there, everything else should hopefully be falling in place. All right, two formulas. We have the distance formula, and we also have velocity at some time equals the acceleration, sorry, it'd be the initial velocity plus the acceleration times time. All right, what's the very first thing we have to solve for in this problem? Just like the last problem we did here on the previous video, we solve for how much time is the ball in the air. So let's say long, I mean time. You must do time. And as I've mentioned, the y component gives us time. This is where I will get the time component. So how long am I going to be in the time? I'm going to be in the air for as much time as it takes for y hit the ground. So I want to figure out the time. I want my time when my position is at xt or s equals 0. Okay? So at this point, I have, let's solve it out here. Now I'm going to do math here. Let's give ourselves a little more room here. Paper. All right. So I'm going to do on the left-hand side here, I'm only going to do math that's in the x direction. Here, I'm going to do math that's in the y direction. All right, so distance equals xi plus vit plus 1/2 at squared. Now, at this point, my distance is going to be my xt. I want to know my position when it reaches 0. I am at 50 currently. My initial velocity, vi, equals, just take that off of there. Right, 1 second, catch up again. 50 plus, okay, now my initial velocity in the y direction is 0. I'm not going down at all. All right, so that whole component flips to 0. Plus 1/2, my acceleration in the y direction is a negative 9.8, and then it is t squared. I want to find t. All right, so let's take a moment. I'm going to, one of the more common problems as well is the signs. Making sure we have positive 50 here, all right, and 0. Subtract it over, I get a negative 50 equals half of 9.8, all right, 4.9. So this is going to be a negative 4.9 t squared. I'm going to divide the 4.9 out and square root it, and that's going to give me my time when my object is at the 0 location, which is when I hit the ground, which is the time I'm in the air. So 50 divided by 4.9. Now two negatives are going to make a positive, and then that's 10.2 square root the previous answer, and I'm going to get 3.19 seconds. All right, 3.19 seconds. Now that's incredibly important because on my table, my time is the same for both of them. That's time in the air is going to be 3.19 seconds. All right. At that point, I just got to remember that the y component gives me how high I am, and the x component gives me my horizontal location. So let's see what some of these problems are asking us to solve for. All right, so this thing wants to know how far did I travel? That's a very common problem with this particular thing. What's the velocity of impact? What's the angle of impact? Okay. So let's go with the first things. How far horizontally did I travel? As I mentioned, that's an x component item. So I want the location at some time. All right, look, that's S equals xi plus VIT plus 1/2 AT squared. Now again, I'm going to get from my picture here, I want to know the maximum distance out that I'm traveling. Well, the harder I throw this thing off the cliff, then the farther it's going to travel. As I mentioned, the x component controls how far out you're going. I am traveling at 15 meters per second, and I will always be traveling at 15 meters per second, and there'll be no acceleration in the x component. So this guy is all going to be 0. A is 0. The t, now what t do I want to choose? It doesn't matter what t I choose. Whatever the maximum t I can choose is 3.19. That's going to give my location right here. But if I choose a t smaller, it's just going to tell me my horizontal location at that time. So this happens to be the farthest location is at the 3.19 seconds, which is what the problem typically is going to ask. They could say, by chance, there's a wall located at this place. How high are you at that location? If I knew my time that I was traveling over the top of this wall, well, then I could just at that point start looking at locations. Now, this is a height, which would require a y location. But either way, it would be telling me the time which I'm over the top of it. And then, of course, so I'm going to use 3.19 for my time. And my location horizontally is just 0 initially. And I'm solving for this guy right here. Okay. All right. So 3.19 times 15. There we go. 47.9 meters. So equals 47.9 meters. Okay. All right. So the last problem says, all right, how fast do I impact the ground? Well, this is not as easy as it looks. The velocity of this thing has actually two components. It has at the very bottom, it has a horizontal velocity of 15, and it has a downward velocity. All right, so let's solve for, and then the resultant of those two vectors is actually my holistic velocity as hit the ground, and this angle right here, okay, you can see the triangle if you want to find the angle of impact. Depends on how they ask the question. Okay, typically they would want to find the angle with the horizontal. Okay, which is the same as this angle right here. All right, so I know that no matter what, I always have the same velocity horizontally, which is 15 all the time. So x is the 15 velocity. So I'm using velocities to get my overall velocity. And what's my velocity up and down at impact? I don't think I've solved for that yet. So let's solve for that quickly. All right, so now this is the y component. Okay. And there's a couple of ways that you can think of this. Okay. If I threw a ball straight up, okay, let's draw a picture of this here, like this, horizontally. Take that back. Let's draw this. I'll draw it over here. Let's say I throw something at an angle like this, okay? And if I throw a ball with the same upward velocity, no matter what I do horizontally, it doesn't matter. If I throw a ball in the middle here, I throw them both up with the same upward vector, then this, regardless, okay, of what's going on horizontally, these two balls will take the same path upwards. When this ball is located right here, this ball will locate here. When this ball is located here, this ball is located here. And they actually would touch very close, right here. They'd be in the same spot. And when they came down, they would be both here. And they would mirror each other because they have the same y component. Okay. So up and down controls is in the y component, and that's what I want to utilize for the velocity at the bottom. Okay. So in this case, you can think of it a couple of ways. I am essentially going to be falling from my max height. My max height is, as we measured earlier, I do that one here yet. Okay. Well, the first thing I did was how long is the ball in the air? I figured that out with the y component. How far the ball traveled did that. Okay, so let's do two more things here. We'll add one more thing in here. Okay. What is my maximum height? And I'll use that when I figure out the rest of this other problem here. Okay. So what is my y component here? My max height is 50. Okay, for this problem. If I did a horizontal throw or a angular throw, then I would use my y component. Okay, but in this one, I have my max height, so it's 50. So if I drop it at 50, same velocity here as would be here. Okay, keep in mind they work independently of each other, x and y. All right, so let's just find max height since that's 50. What is my velocity at the bottom? We'll get that pretty quickly here. Okay, so VF equals VI plus AT. All right, now this particular thing is in the air, 3.9 seconds. All right, so it's going to be velocity initial in the y direction is 0. Initial acceleration is negative 9.8. And I have a time of 3.19 seconds. All right. Multiply that together, and I have my velocity at that time. 3.19 times 9.8, and there we go, 31.6. All right, VF equals 31.6 meters per second. Now again, that's only in the y component, 31.6. So my angle is constantly changing as I go along here because my y component is getting faster and faster. All right, let's find our total impact velocity. Let's do that right here. You should be pretty familiar with now. This is a Pythagorean theorem question. So 15 squared plus 31.6 squared. And then we'll square root that guy to get my total impact velocity. And I'm getting 34.9 meters per second. So this guy right here, 34.9 meters per second. Okay, that's my impact velocity. I want this angle here. Angle of impact, same as this guy, pretty common. Coming more and more straight down. Okay. What I want to do is use a trig function here. So I'm looking for this angle. Let's use the two that are original. So I'm going to use the tangent of my angle equals opposite, which is 31.6, and then I have 15 is the adjacent. And I'll inverse tangent that thing to get my angle. 31.6 divided by 15, inverse tangent, that particular angle, and I'm going to get 64 degrees. All right, and that ends pretty much anything you could want to do with this particular type of problem. Our next problem will be at an angle where you're throwing at an angle and you got to solve out. All right, all the same questions, just at an angle. Thank you very much.